Hello, everyone. I hope you started a great day. Let's start today's discussion. Today, we are going to talk about the time response system. We kind of like talked about it a little bit when we wanted to like develop either the transfer function in S domain, the model of the system in S domain, or when we talked about the state space, when we tried to develop the model of the system using the differential equations in a time domain. But today, in this discussion, we are going to go a little bit deeper in time response, uh, what that means, what are the characteristics of a model that could influence the time response of a system, and see some example to get a proper understanding of the behavior of our system in response to any type of input. Now, work with me. Okay. Basically, when you actually develop the mathematical model for your system or subsystem, okay, it could be, as we said, a transfer function in S domain or the state space in a time domain. You have to analyze that system, the response of that system in two steps. One would be the transient state response, and another one is the steady state response. Okay? Now, those response, those response are the summation or the collection of two types of response. One, we call it natural response, which is caused by the dynamic or characteristics of the system its own. Okay, and another one is force response, which is the response that is the result of applying an external input into our system. Okay, so we have natural response, which is caused by the characteristics of the system alone, and we have force response, which is the result of applying an input to our system. Now, so far we talked about the transfer function. We are going to focus a little bit on transfer function more than a steady space when we talk about this time response. You already saw that a transfer function of a system, especially when we have a complex system or like a feedback loop in our system, the transfer function normally is in a shape of like a denominator over the denominator over a denominator. So we have two functions that are divided by themselves, and it creates a transfer function. Now, we want to introduce in this chapter two new concepts. One is the concept of the pole, another one is the concept of the zero. Now, when you have your transfer function, okay, the numerator and the denominator are some algebraic equation, okay? It could be first order, second order, or nth order equation in respect to S. Okay? Now, the zeros, when you solve the denominator to find the zeros of a denominator of the transfer function, those zeros of a denominator, we call it pole. Okay? So they are actually the values of S that make the transfer function go to infinity. These are the S's that make the denominator zero, so the transfer function goes to infinity. Is that clear? Now, the zeros are the roots of the nominator, which you can imagine that the zeros are the values of S that makes the transfer function to become equal to zero. So they are the roots of nominator in your transfer function. Are we good? So very simple concept, very simple kind of like definition, but they are very important when you want to like evaluate the dynamic of the system. Now, let's look at an example. Let's say we have a transfer function. We have a transfer function when our T of S is S plus 2 over S plus 5. And we have the input of the step function, which is 1 over S. Are we good? Okay, now we want to see what are going to be our output, which is the response of a system. Okay, and how we can define those output and find out what are the zeros and poles for that output. Now you can see that I already applied the input to the transfer function. Okay, so I developed the output in S domain. When we have the function for our output, we know we want to use the linear characteristics of a Laplace transform. Okay, so we are going to separate all the terms in a denominator. So we are going to have one term which has a denominator of the S and another one that has a denominator of S plus 5. Are we good so far? And we already know how to find the A and B. So I don't want to like take a lot of your time repeating those concepts. So if you do that in this example, you are going to see that our output is going to be 2 over 5 divided by S plus 3 over 5 divided by S plus 5. Now, look at the denominator. What are the zeros of the denominator? The zeros of the denominator here are denominator. Yes, -5 and 0. Okay, so if you wanted to like have an S-plane, okay, a graph of S-plane, you have a 0, which we normally show it by a cross, okay, by like you can see that it's X or cross, okay, which we have 1 0 at -5 and another 0 at 0 itself. Are we good? Now look at the denominator of the output. Sorry, these are the poles. Sorry, the poles we show it by cross. Okay, now look at the denominator. The 0 for the denominator, you can easily find that is -2, right? So we have a -2 in S domain. As a 0, we show it by a circle. What that means, we already know how to find the C of t using the Laplace inverse of these separated terms. Are we good? So this one is going to be 2 over 5. The Laplace inverse of this is going to be 2 over 5. Correct? Are we good? And the Laplace of this one is going to be 3 over 5 times there is a frequency shift e to the power of -5t. Are we good? All of them times ut. This is what we learned before of how to use the Laplace inverse to find the values, to find the time domain function using the S domain function. Are we good? Yeah.
I guess I didn't catch this. How did we determine that on the system 0, there would be a negative? Is that -2?
-2. Here, look at this S. The S is S plus 2 over S times S plus 5.
Okay.
Okay, so we have a 0 on -2, and we have two poles on 0 and -5. Now, before, as I said, we used the Laplace inverse to do that. Now we have an easier time to find the response of the system. Now, look at this. We have an 0 in S. Okay? So what we are going to have is this coefficient, which is the limit of, we wanted to like have a for S to 0, which means S times CS when S goes to 0. If you put that here, it becomes 2/5. And another pole, which the coefficients is going to be limit of S plus 5 times CS when S goes to -5. Are we good? Which if you put the numbers is going to be 3/5. Are we good? Now, so using this formulation, we can find the coefficient. How we can find the function itself, the time function itself? We are going to always have an e to the minus something t. For the first pole, the s is 0, so that something that we call b is going to be 0. E to the power of 0 is 1. Correct? So the first term is going to be 2/5 times 1. The second term, the b is 5. Okay, let me put that b here. The b is the 0. The 0 is -5, sorry. Okay, so it's going to be whatever coefficient that we have at s to the -5 times e to that pole times t, which is e to the power of -5t. Okay, so without Laplace inverse, just by finding the poles of our transfer function, okay, we can easily find the time response of our system. Is that clear what we did? Are we understand? Now, let's do another example. Yes, this is the time response. We wanted to like see what is the time response. We already know the model of the system. Now we want to see, okay, if we have like a step function as input, what would be the result at the output in time domain? Very good. Any other question? No? Let's move on to the next example. Here, I have a more complex transfer function, which is s plus 3 over s plus 2 times s plus 4 times s plus 5. Okay? And my input is still a step function, 1/s. From the discussion that we have before, we know that the result of CS is going to be a coefficient over S, which is one of the terms in the denominator, another coefficient over S plus 2, another coefficient S plus 4, another coefficient over S plus 5. That was the use of the linear characteristic of Laplace, right? So we have that. Now, the term, you remember we said is going to be the fourth. We are going to have forced response and a natural response. Okay, and we said the forced response is caused by the input, and the natural response is caused by the system itself. So whatever terms that we have that is related to the input, this is the forced response of our system. And whatever term that we have that are not related to input, that are not caused by the input, It is solely caused by our transfer function. It's going to be the natural response. Now, so far we used the previous discussion. Let's actually draw poles and zeros in S domain. Now, here, our output, our C of S is going to be S plus 3 over S, S plus 2, S plus 4, and S plus 5. Are we good? I just applied the input to the transfer function. Now look at this. The denominator has 1, 0, which is minus 3. Okay, so let's say 1, 2, 3, 4, 5, 6. Okay, so we have 1, 0 at minus 3. Are we good? And we have 4 poles here, 4 poles, one at 0, another one at minus 2, another one at minus 4, and another one at minus 5. Are we good? So we are going to have the term that we are going to see in our C of t using just the plot, okay, is going to be something times e to the power of 0t. Okay, plus something times e to the power of minus 2t, plus another thing with the coefficients minus 4t. Are we good? Plus another term which is related to this pole, and it's minus 5t. Okay? Now, what are these coefficients? These coefficients are, like for example, for the 0, we talked about that, is the limit of S. 0 is related to the 1 over S, so it's going to be S times C of S when S goes to 0. You put the numbers, you are going to see what is going to be the value. Okay, which is going to be 3 over 6, 5, 11. So here we are going to have 3 over 11. Are we good?
Wait,
The coefficients of S0, okay, is S itself. See, S, this term, the 0 of S is 0. Correct? And we want to find the coefficients of the one that has a pole in 0. So we are going to multiply our S domain function by S. Are we good? And then limit the whole result to that pole, which is S limits to 0. So if you multiply that by this function by S, this one is going to be kind of like eliminated. And you put S equal to 0, so it's going to be 3 over 2 plus 4 plus 5. Right? So now let me do another coefficient with another color. Oh, yeah, sorry. 2 for 8 times 5 is 40. Thank you, sorry. Now, e to the power of 0 is 1, okay? So we have one term, which is equal to the 3 over 40. Now, let's talk about the other pole, S minus 2. Okay, the pole minus 2. This is going to be the limit of S plus 2 times the CS when S goes to the minus 2. Are we good? Now, if you do that, now this one is going to be eliminated. So the CS, we put minus 2. Minus 2 here is going to be 1 on denominator. This is minus 2 times plus 2 times, so it's minus 2 times 2 times 3, which is going to be what? Minus 1 over 12. Are we good? So the coefficient here is minus 1 over 12. And you can find the rest of the coefficients similar to that. So instead of getting a Laplace inverse, you can simply plot the zeros and poles and find what is going to be the time response of the system. Is that clear what we did? Any question about that? The second term? Yeah. We want to find the coefficients that is related to the pole minus 2. Okay? So we are going to multiply the CS by the denominator responsible by that pole. Okay? So if you multiply the CS by S plus 2, then you are going to have, let me rewrite that, CS S plus 2 times CS is going to be S plus 3. You are going to have an S. This S plus 2 is eliminated times S plus 4 times S plus 5. Are we good? Now, we want to S to be minus 2. So we limit the S to the minus 2, meaning we put minus 2 as instead of S. And it's simply like the denominator is going to be minus 2 plus 3, which is 1. This one is going to be minus 2. This one is going to be 2. And this one is going to be 3. Is that clear? Now we just multiply these with each other, which is going to be minus 4 times 3 minus 12. So the coefficients of the term related to the pole minus 2 is going to be minus 1 over 12. Are we good? Now, again, you can find the coefficients of e to the power of minus 4t and e to the power of minus 5t in a similar way. Any question? No, the poles on zeros are very important. After the midterm, when we wanted to like analyze the stability of the system and run like a Nyquist and everything, these are these, especially the poles, okay, are the factors that defines the stability of your system. We are going to talk about that later. So it's important. Now, another example. This is our transfer function, and we are going to apply a step function as an input. So, denominator is going to have two zeros, one at minus 4 and another one at minus 6. 1, 2, 3, 4, 5, 6, 7. So 1 at minus 4 and 1 at minus 6. Are we good? Now, and the denominator is going to have four zeros, the transfer function itself. 4 zeros at minus 1, minus 7, minus 8, and minus 10. So we have 2 zeros and 4 pole for the transfer function itself. We didn't apply the unit yet, the input yet. What would be the input add to this both plot, to this pole 0 plot? No, the input. the C of S is going to be RS times GS, right? So if you multiply this GS by 1 over S, what would be added to our plot? A pole at 0. So we have a pole at 0. Okay? Now, if you run the same analysis, so we know that the C of t is going to have one term that is a coefficient, one coefficient times e to the power of 0t, which is 1. Another term with the pole minus 1. This is related to that one. Another term for the pole minus 7. Another term minus 8. And another term for minus 10. Are we good? Now, how to find the coefficient? Again, we know. This one, the A, is the limit of S times C of S when S goes to 0. The B is S plus 1 times C of S when S, this is the limit, sorry. When S goes to minus 1, the C is the limit of, what is? S plus 7 C of S when S goes to minus 7. And you can find what is the, you can imagine what is the D and E's. Are we good? So very easy. We don't need a Laplace transform. We don't need even like to separate those terms and find the denominator for the separated terms. We just simply can use the plot and those limits and find the C of t very easy. Are we good? Now, you can imagine when we say force response, and I wanted to like for you to understand when we say natural response and force response. Okay, we said natural response are the one that are related to the poles of the system itself, the GS itself. So these parts are the natural response. Are we good? And the one related to the input, which is this part, the S0, is the forced response. Sorry? That's the point. Yeah, I wanted to like mention that. Okay, so whatever is from the input is the forced response. Whatever is from the GS is the natural response. Now, we said we are going to have a transient state time response and a steady state time response. The steady state is when the t goes to infinity. Are we good? So what happened to the C of t when t goes to infinity? All those exponential become 0. What will remain is the forced response. So when we talk about the steady state, we talk about the forced response of our system, of our output. And what is the transient response? What is going to be the transient response? The A is the forced response. It's what's going to remain, okay, when t goes to infinity. The forced response is the input, okay? When t goes to infinity, all those exponential become 0 because they have minus power in them, okay? What remains in infinity is just the A, which is the one that are related to the input. So that A is in this example is your steady state response, which comes from the force response. Now, my question is, we have another state, transient state response. What terms defines or shows the transient response? A little bit louder, sorry. T goes to zero. T goes to zero is initial condition. Make sense? T goes to zero is the initial condition. Now, what is the transient state? Meaning from the T bigger than zero all the way to infinity. Okay, that's gonna be transient state. Now, which of these terms, A, B, C, D, E, times their own exponential, which of these terms would participate in transient? All of them. When t is equal to 2, what is going to be the C of t? What is C of 2? It's going to be A plus B e to the power of minus 2 plus C e to the power of minus 4t. Okay, C of t when t goes to 2, which is one of the time in a transient, is going to be A plus B e to the power of minus 2 plus C to the power of minus 14 plus D to the power of DE to the power of minus 16 plus E times exponential of minus 20. Does that make sense? We just put T equal to 2. In the transient, this force response is not eliminated.
The transient is just all
of them. A steady state is the one that all the exponential is already becomes 0 in infinity. Make sense? Is that clear? So do not make that mistakes of eliminating the force response from the transient. You remember when you have like a RC system, okay, when you have a RC system or RL system, the response is going to be 1 minus that exponential. That 1 comes from the force response. Are we good? So, any question? Now, another example. We are going to have a GS as shown in the slide and a step function as the input. Now, without even like going through the Laplace transform, okay? We are going to simply plot what we have. Minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, minus 10, minus 8, minus 7, minus 1, minus 4, minus 6. Okay? Now, we have a 0 at minus 4 and a 0 at minus 6. G of S has a pole at minus 1, minus 7, minus 8, and minus 10. And our input would add a pole at 0. Okay? So the response is going to be a certain coefficients, let's say A times e to the power of 0, which is A, plus the coefficients times this pole, which is e to the power of minus 1 times t. Another term for this pole, so we have a coefficients times e to the power of minus 7t, d to the power of minus 8t, which is related to this pole, and then e to the power of minus 10t, which is related to this pole. Are we good? Now, what is happened? Let me see if I. Oh, you know how to find the coefficients. I don't want to like go through that. This is finding the coefficients. Let me explain that later. I don't want to confuse you. Okay. Is there any question so far? No? Okay. When you talk about the system, the most common system that you're going to see, okay, is either the first order system or second order system. The first order system, the general transfer function of first order system would have, it is on the name, would have one pole. Okay? So, for example, in this example that we have, the standard representation is A over S plus A. We don't have any zero. We only have one pole at minus one, minus A. So what's going to happen is if we have a step function as an input, which adds another pole at zero, okay, our C of t is going to be the term related to that zero, which is a function, the forced response of a system, which when you have like a step function, this is going to be a constant number, like A. And then we have the natural response of a system, which we know we have one pole for the natural response. It is minus A, so it's going to be a coefficients time e to the power of minus 80. Now, why the coefficients here is 1? Because the limit of S CS, S goes to, no, S plus A times CS, S goes to minus A is going to be 1. Put those in here. Is that correct? Is that correct? What is the coefficients of e to the power of minus 80? It's the limit of C plus AT. So it's going to be A, S plus AT, S plus A, cancel the denominator. So it's not going to be 1. It's going to be A. Are we good? Did you see what I did here? This is the coefficient related to the pole minus A. We said for defining the coefficients of pole minus A, we are going to find the limit of the term for the minus A, which is S plus A, times the C of S, okay, which is the limit of S plus A times A over S plus A, when S goes to that pole, minus A. These two cancel each other out. There is no S, so it's always A. Make sense? Are we clear? What happened here?
You'll put the value of negative A, place it past.
There is no S. These two cancel each other out, so it's going to be only A.
So now you're still at split A.
Oh, yeah, sorry. Yeah. And it become, yeah, 1. I thought I made a mistake. Negative, yes. This is here, -1. Are we good? Now, we have an A in our transient state. Anyone can tell me what is the significance of A? What that A do in our time response? How fast to what? What do you mean how fast? Fast what? What is fast? What terms in the response you call it fast? What characteristic you call it fast? How fast? Yes. All right, let me rephrase. Kind of like rephrase that. How fast the transient state would decay and system goes to a steady state. Does that make sense? In theory, we said the steady state is t equal to infinity. It's not gonna. In reality, we don't have infinity. So that A defines how fast we are gonna reach approximately the final value, which is our steady state. Does that make sense? Now, what if the t is equal to 1 over a? If the t equals to 1 over a, e to the power of minus at become e to the power of minus 1, which is 0.37. So the output, which is 1 minus that exponential, is going to be 0.63. Are we good? Does it ring a bell? Anywhere you heard that this is the input, our input is a step function 1. So 1 times u of t. Okay, so this basically means we are at 63% of our final value. Our final value is 1. At t equal to 1 over a, we are at 63% of our final value. Anyone remember any type of parameter that you know, any concept related to the 63% of the final value from the circuit 1 or signal and systems or any type of like signal analysis that you have? It is the time constant of system. The one that you normally call it tau. Remember? So whatever you have in a first order system, whatever you have here as A, which is the coefficients of the t in the exponential of the, in the power of the exponential, 1 over that number, 1 over A is going to be the time constant of your system. And what is the significance of the time constant? Do you remember what we called the time constant? How the time constant would actually, we could use the time constant to find values, the specific values in our output. What is the 5 tau? When we get to the 5 times time constant, what would we get? What would we get at the output? The force is 1. What would happen if we are at t equal to 5 over a? Do you have a calculator? Find what is the exponential, what is the e to the power of minus 5? Anyone was able to calculate that? Zero point 99. 99% of our final value. Are we good? So this is what we call, we never gonna reach the final value, that 1, because we don't get to reach the time infinity when the exponential becomes 0. In practice, we consider any time after the 5 tau close enough, so that's going to be our steady state. So this is the significance of the tau. 5 tau, after 5 tau, we are at a steady state. Approximately, we reach the final value. Are we good? So this is when we want to talk about the transient state and a steady state response, this is the significance of the time constant. Any question about that? Let's say we don't have the let me see if I have another slide. Let me go through that first, this definition, and then we talk about the concept I want to. We know what is the time constant. The time constant is the time that we reach the 63% of final value. This is final value. This is 63%. The time it would take us is tau. Are we good? Now, for first order system, we have another concept named raise time, which is defined when we go from 10% to 90%. From 10% to 90%. This is the rise time. Are we good? I'm just making definitions. And the settling time, is when we reach the 20% margin from our final value. So this is the 98%. This is the settling time. Now here is 5 tau, which is 99%. Now the settling time is normally 4 time constant. Are we good? So the rise times is from 10% to 90%. And approximately is 2 time constant, but not exactly equal. You can see that. It's a little bit more than 2 time constant. The settling time is 4 time constant, which we reach the 98% of our value, our final value. And the steady states happen after the 5 time constant when we reach the 99% of our final value. These are the definition. Okay? Any question about that? Sorry? Never. Because if you wanted to get 100%, t should goes to infinity, which we never go to that point. Any questions so far? No? Let's say we don't know what's inside our circuit. We know that it's a first order, okay? And we know that because of the measurement, we kind of like measure the output. We apply a step function to the input of a black box, and we measure the output, and we see such a curve. Okay? This is like, for example, a waveform that you see in oscilloscope. How you can find the transfer function out of that measurement? You know you are going to have a force response in the C of S in the output, which is related to the input itself. Input is a step function, so we are going to have a term in our CS, which is a coefficient over S. Are we good? This is the force response that we talked about. And you are going to have another term in the first order that is related to the transfer function itself. Are we good? So let's look at this. This is, we know by the shape that is the first order, because it's just one exponential. Are we good? Now, we can measure the time constant of this signal. So if you measure how much time it took our waveform to reach the 63%, we have our time constant. Are we good? Now, if we have our time constant, that means, and it is like 1 over A, that means we have a term in our output which is minus AT. Are we good? Exponential of the power of minus AT. Now, let's go back when we talked about that plot that we plot the zeros and poles. Okay? What conclusion you could have if you have an exponential with the power of minus AT? I wanted to like plot the zeros and pole. For input, I know that I have one pole on 0, right? Now I know, because of the time constant, that I have a term e to the power of minus AT. How you can show that term in the S plot? We are going reverse of what we did before. We draw the S plot and we find the C of t out of that S plot. What in S plot would cause having such a term in our time function? Pole at minus A. So we are going to have another pole at minus A. Are we good? What that means? That means the denominator of a transfer function has a term S plus A. We don't have any other poles, so it's going to be the only pole in our transfer function. And we are first order, so whatever transfer function we have, g of s, is going to be a constant number in a denominator and s plus A. Are we good? Now, how we can find this coefficient? We know if we separate this term, now I call this coefficients k, let me do that to be consistent. So this is going to be our CS. 1 over S is our input, and we already see from the graph that our transfer function is going to be a constant over S plus A. Okay? If we separate them and find I find the denominator for the separated term, we are going to have K over A over S minus K over A over S plus A. We already know how to find them. Is that okay? This one is the limit of S times C of S when S goes to 0, which this would cancel each other out. S goes to 0 is K over A. Are we good? And this one is S plus A times CS, which is K over S when S goes to minus A, which is minus K over A. Are we good? So, look at this. This is the force response, which in C of t is going to be K over A times e to the power of minus 0, which is K over A itself. This one is minus K over A times that e to the power of minus AT. What is K over A? We talked about that. What is if t goes to infinity, this one eliminated, only this one remain. What is K over A in that graph? The final value, the steady state. Are we good? So here, my final value is 1. It could be any number. So K over A is the final value. And from the curve, I already know what is the A. So I can find the K. Are we good? And if I find the K, I have my function of the C of t, and I have the transfer function of the system. Does that make sense? This minus also is in the transfer function, so be careful about that. Are we good? Any question? Is that clear how we reach that transfer function from the measurement? If you have any question, please ask, because yeah. Yeah, let's go another time. Which one? No. Let's go another time. I want to make it very clear because this part actually is the one that you gonna use and when you want to do an actual, engineering analysis outside. Because normally it is not easy to find the transfer function of a complex system, but you can have a step input and you measure the output and you see what's going to happen and find the transfer function. Okay, now I said that I applied a step function to my system. So if that means the C of S is at 1 over S times G of S. Are we good? Now, looking at the plot, I can find the time constant, which is the time that it took the plot to reach the 63%. Are we good? That means I have a term in my C of t. I have a term that say A times e to the power of minus AT. 1 over A is time constant. So I would have such a term in my time response. Are we good? Now, let's go back to the S domain plot. In S domain plot, I know that I have a pole at 0, which is because of my input. And the rest of the system only created a pole at -A. It's a first order system. Are we good? So what's going to happen? I am going to have a pole in -A. Therefore, my C of S are going to have a constant number at denominator, that input, and that pole in -A, which determine Laplace of the CS is going to be S plus A. Are we good so far? Now, I have the A because I have the time constant, which is 1 over A. All I need to do is to find this K. So I would have the whole transfer function, and then I would have the full Laplace of output. So I know the input, I can have the transfer function. If you separate these two terms, you are going to see that these would separate to K over A over S minus K over A over S plus A. Very good. This K over A is going to be this minus K over A is going to be the coefficients of e to the power of minus AT, and K over A is going to be the forced response or a steady state of my system. Are we good? My steady state is the final value. So whatever final value I have is going to be K over A. I have the A, I can find the K. Are we good so far? Now that I have the K, this is going to be my CS. I know this S is for the input, so my transfer function, G of S, is going to be the rest, which is K over S plus A. So I find my transfer function from the response of a system. Are we good?
We determine CS then K.
This is the CS. Okay, we want to separate these two poles. We are gonna have what we are gonna have is a constant, let's say alpha over S plus beta over S plus A. Correct? Now, what is the alpha here? It's the limit of S times C of S when S goes to 0. Okay? So S times this one is going to be K over S plus A, right? S goes to 0, so it's going to be K over A. And same for this one. The limit of S plus A times the C of S when S goes to minus A, it would eliminate this pole. So we are going to have K over S when S goes to minus A. So this one is going to be minus K over A. Are we good? What time is it? No, okay. I don't want to start second order because it's going to take a lot of time. And it's very important actually because you are going to see a lot of second order system in your system, in your analysis and your circuits. So this is for today. I am going to stop here. And in the next time, we are going to talk about the time response of the second order system. And hopefully we are going to finish the conversation by introducing the eigenvalue and eigenvectors and see how they are related to what the time response that so far we discussed. Are we good? Any question? No? Okay. Thank you very much. I hope you are going to have a very good rest of the